How's everyone doing? Are there any questions, concerns? All right. Okay, so we're going to start already. I wanted to make one or two quick announcements. If anybody reads an extension on assignment 1, please write to me privately today by 5 p.m. Okay. And then if there is a good number of students who need extension, I may give an extension of 1 or 2 days. Otherwise, I will be willing to give individual extensions depending on the circumstances, with or without penalty. Okay. Good. And what else? Right. Yeah, there was a question on Piazza about, I think I've mentioned it in my last lecture maybe, about drawings. So you can use some package. If I find the time today, I'll try to post some information on Tix package, which you can use for this assignment or a future assignment. But you can very well just make drawings that are neat and clean on a sheet of paper, take photos and just import into your LaTeX file. Okay. So that's only for the drawings. Everything else should be typeset in LaTeX. Okay. There was an announcement regarding a correction on the assignment. So I think it's a problem. Can someone remind me? It's problem 1, part C? No, it's not problem 1. It's problem
3D, if I'm not wrong.
3D. Okay, 3D. Thank you. On problem 3, part D, we are defining a set, which is a subset of the edge space. Actually, it's not a subset of the edge space. It is in fact a subset of the cycle space. So wherever you see edge space, replace it by cycle space. Okay. I have posted an announcement on Piazza. So if you haven't seen it, please go and check it out. I will post a corrected version of the assignment. I haven't found the time to do that because I was not traveling with my laptop or tablet on the weekend. Okay. All right. Any other questions or concerns before we get started with today's lecture? Okay. All right. Also, if there is anyone who is still looking for or wanting to have a collaborator and hasn't found one, please reach out on Piazza or just write to me and I will try to find you a collaborator if I can. Okay. Good. So with all of that, let's get started. So in the last lecture, we discussed that we were going to discuss 2 decompositions of graphs in today's lecture, the block decomposition and the year decomposition. So the block decomposition is actually is a very popular decomposition that most of you, perhaps all of you, would have seen in a previous course, especially if you took MA 213 or equivalent. So I'll show it to you by example, but I won't prove details about it. Okay. We'll focus more on year decomposition. We'll actually prove things about year decomposition. Okay. So let's go back to our example that we had in the last lecture. So it's a slightly big example, but it illustrates all the features quite well. Okay, and I just want to remind you what is a non-separable graph. A graph is non-separable if it is connected and it has no separating vertices. Okay. And so if you look at this example here, there are separating vertices here. Let me mark them by darkening them. V1, V2, V3, V4, V5, and there is a vertex. Oh, I see. I forgot to make one loop here. So there is a vertex here that is a separating vertex, but it is not a cut vertex. So that one is V6. So now we are focusing on the separating vertices. If your graph is loopless, then these two concepts are the same, separating vertices and cut vertices. Okay, so these are your separating vertices in this graph. And now what we are going to do is we are going to define blocks of the graph, which are maximal non-separable subgraphs. So just to remind you, what is a component of a graph? A component is a maximal connected subgraph, right? And so in this graph, the components are clear. This is one component, and this is another component, right? Good. In a similar spirit, blocks are nothing but maximal non-separable subgraphs. Okay? Some water. And so if you look at this drawing here, it's quite easy to visualize the maximal non-separable subgraphs. Let's just do that with different colors. I won't use 10 different colors, but I will use different colors for blocks that are close to each other. So here you have one block. Notice that you cannot add anything else to this block because otherwise it will be either it will be disconnected or it will be connected and it will have a it will have a separating vertex in the subgraph. Okay, this is another block here. Let's label these maybe, and doesn't matter. Let's here is another block, and then let's put some more colors maybe. Here's another block, orange colored. It includes this edge, so it is both the edges, both the parallel edges. Here is yet another block, just that loop along with the vertex. So when I'm showing blocks as edges of the graph. So that is one way to visualize blocks. It is a decomposition of the graph. So every edge is going to be in exactly one of the blocks, right? So it is a decomposition in that sense. Alternatively, you can also view blocks as subgraphs. So you take the edges and then you take whatever vertices that are any vertex that is an end of any of those edges, right? So that's fairly straightforward. Here is another block, just this loop. So a loop is always a block by itself. Okay, and then let's see. Here's another block. And then you have one more here. You have another here, orange colored. And then you have, let's say, let me put this in green color. So it seems that we have 10 blocks here. Let me just use black to put all the labels. B1, B2, B3, B4, B5, B6, B7, B8, this big blue colored block. Oh, I forgot to mark one edge. Sorry. This edge is part of the blue block. B9 and B10. Notice that every edge has been included in exactly one of these 10 blocks. Okay? And in that sense, uh, this this notion we are discussing is a decomposition of the graph, right? I want you to recall the definition of a decomposition. A decomposition is you think of, you partition the edge set in such a way that each part will have at least one edge and every edge will be covered exactly once. Okay, so this is the block decomposition of the graph. And as I said earlier, I expect you to have seen this in a previous course. So I'm going to put down a proposition without proving it. But if you haven't seen the proof of it, you may very well try proving it yourself, or take a peek at the text and still try proving it yourself. So for any graph, any two blocks have at most one vertex in common. If you view the blocks as edge sets, they comprise a decomposition of the graph. And finally, if you look at any cycle of the graph, it will have to be contained in exactly one block. It cannot go between two blocks. Okay. Okay, so I'm just going to say proof, do it yourself. Are there any questions so far?
Sir, can we make part is stronger by saying at most one vertex is common and that will also be non-separable? So that will also be sorry, will it be a
Separating vertex.
separating vertex? Sorry, yeah, sorry.
Yes, yes, you are right. So you can make another comment here, and each such common vertex is a separating vertex. Thank you. So that is correct. Okay. And you can visualize this proposition in this example, for instance, if you like. Right. And now what you can also do is you can define a, a bipartite graph, which is not only going to be bipartite, it is actually going to be a tree called the block tree of the graph. Okay. And the way you do it is, this is a slightly big example, so I won't make the whole. Okay, let me actually see if I can copy this drawing and paste it below. No, let's see, how do I do this? No, I want to make it bigger. No, 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 no. Undo. Okay, never mind. Um, okay, I'm having some trouble getting my All right, so what I'm going to do is I'm just going to maybe show you this example. So what you can do here is, okay, this is good enough, I hope. So we are going to make a tree out of this. In fact, let's put it as a bipartite graph. The fact that it is a tree follows from the proposition that we have just discussed. So what you can do is you can put all the blocks on one side. You can put a vertex for each block. So we are going to make a different graph from the given graph. And I won't draw this whole graph because the example is a bit big. Okay, so we have the blocks of the graph on the left side, and we have the separating vertices on the right side. Okay, and whenever a block contains a particular separating vertex, we are going to put an edge between them. To give you an example, if you look at this blue colored block with 5 edges, B9, B9 is it contains 3 separating vertices, V3, V4, and V5. Okay, so I'm going to join B9 to V3, V4, and V5. Okay, and similarly, for instance, the block B5, which is a loop, contains just one vertex, which is V6. So B5 is joined to V6. And likewise, you can complete this whole graph. Let's do a bit more. V1 is part of B1 and B2. So V1 is part of B1 and B2. Okay. V2 is part of B2, B3, and B4.
Sir,
Go ahead.
sir, why B1 is part of B1 and B2?
Sorry, can you repeat it?
Oh, no, no, sorry, it is my mistake. Okay, I
Yeah,
got it.
yeah, it's a bit confusing between the V's and the B's. Sorry, not the best choice. Okay, right? So you get the idea, right? Whenever a block contains a vertex, you make the corresponding vertex for that block and the cut vertex and the separating vertex, sorry, you make them adjacent. Otherwise, they are non-adjacent. So anyways, this graph here is incomplete because I don't want to waste time on completing this graph. Okay, but you get the idea. For this graph G, we get the um, block tree of G. Okay, the fact that this is a tree follows from part C here. If there were a cycle in this bipartite graph, you would be able to find a cycle in the graph G that would be part of at least 2 different blocks, and that is not possible because of part C. Okay, so this ensures that the block tree is indeed a tree. Okay, good. Okay, there are a few more things I want to define based on this tree here, because some of these things may be relevant on your next assignment. Okay, so once you have this tree, you can define the concept of an end block. An end block is a block which is a leaf in this tree. So let's just put that down. Um, if G is separable, then blocks of G which correspond to leaves of its block tree are called its end blocks. Okay, when is it going to be a leaf? When that block has precisely one separating vertex, right? So can someone tell me what are the end blocks in this graph G without constructing the tree by just looking at the graph itself? What are the end blocks here? Okay, let's see. Someone's typing. Arnav? Yes, go ahead.
B1, B5, B6, B10, B7, B8.
B1, B5, B6.
B10.
Okay, and B7, 8, and 10.
Yeah.
Right? Okay. Does everybody agree with that? Does anybody see another end block that has not been named yet? Right. So these are all of the end blocks. These are all of the blocks that contain exactly one separating vertex, which is why they are going to be leaves in the corresponding block tree. A leaf is a vertex of degree 1, right, in a tree. Good. All right. So these are the end blocks, and in an end block, you have two types of vertices. There are the separating vertices, and so this is actually true for any block. Okay. So for any block, you have either the separating vertices or you have some internal vertices. So let's just define that. So an internal vertex of a block of a graph G is a vertex of the block, of course, which is not a separating vertex of the original graph. Okay, so let's do one example here. Can someone tell me what are the internal vertices of the block B2? What are the internal vertices of the block B2? Well, B2 has only two vertices, V1 and V2, and they are both separating vertices, right? So B2 does not have any internal vertices. What about B9? Can someone tell me if B9 has any internal vertex? Does B9 have an internal vertex? Yeah. Yes, exactly. And that is this vertex here, which is not a separating vertex, right? So I put a circle around it. So this is an internal vertex of B9. Okay, good. All right. So, okay, and why do we care about blocks and the block tree of the graph? The main point here is, let's just call this the key takeaway. And I'll give you one example of it, which will be again a do-it-yourself exercise. So one can usually reduce the study of all graphs to the study of their blocks. So what do I mean by this? Let me give you one example. Using proposition 5.3, you can prove the following. A graph has a cycle double cover. Hopefully everyone remembers the cycle double cover conjecture. A graph has a cycle double cover if and only if each of its blocks has a cycle double cover. Okay, so this is a do it yourself. That's not too difficult, to be honest. The point here is that because of this observation, in order to prove the cycle double cover conjecture, you can restrict yourself to non-separable graphs. If you prove it for non-separable graphs, then you would have proved it for all graphs. In order to prove the CDC conjecture, one may restrict themselves to non-separable graphs. In fact, something much stronger is true. You can keep reducing this to more and more connected and specialized graphs, but we might see that later in the course. So the first step is, instead of looking at all graphs, just look at non-separable graphs. Okay, and this happens in almost all problems in graph theory, or most problems in graph theory. You don't need to deal with all the graphs. You can restrict yourself to non-separable graphs. Sometimes you can restrict yourself to even more connected graphs, like three connected graphs, as we will see soon in this module, right? So that is one of the key features of structural graph theory, and one of the key reasons why connectivity plays such an important role in many areas of graph theory. Okay. Okay, good. So that's all I want to tell you about blocks and block decompositions of the graph. All right. Are there any questions? No questions or concerns? Okay, so in that case, let's move on to our next topic for the lecture today, which is ear decompositions of non-separable graphs. Okay, so here is the reason for studying this. So now we know that, for example, for cycle double cover or many other problems in graph theory, you just need to deal with the non-separable graphs. Many proofs in structural graph theory are based on induction, right? What's the problem now? You have a more specialized class of graphs, and let's say you want to prove something using induction. But then you need a way to remain within this class of graphs. So what you want to do is you have a big graph about which you want to prove something by induction. Let's say this big graph is a non-separable graph, right? And you're trying to prove a statement about all non-separable graphs. What you want to do next is you want to get a smaller non-separable graph from this big non-separable graph. So you need some tools to do that, right? If you just remove something from a graph, from a non-separable graph, the resulting subgraph may not be non-separable anymore. So you need to be smarter in removing stuff from the graph to get a smaller non-separable graph, or more generally to get a smaller graph in the same class of graphs. And this is the spirit in which we are going to study ear decompositions of non-separable graphs. Okay. So this is going to be our first. There is a reason to think of these induction tools as generation theorems. You will soon see why. Our first generation theorem, you may think of that as an induction tool. Okay. And that is the ear decompositions of non-separable graphs. Okay, good. So let me start by an example straight away and give you an idea of where we are going. Okay, so let's see. So I want to take the Peterson graph, which is a non-separable graph. And I want to show you how one would construct it using this ear decompositions. So we are going to generate the Peterson graph from a small non-separable graph. Okay, so here is the Peterson graph. What I want to do is I want to start with a cycle. Notice that the cycles are the simplest non-separable graphs, in the sense that you cannot remove anything from a cycle to get a smaller non-separable graph. Okay, there are other such graphs, but they are very small, like K1 with a loop, which is a cycle, K2. But once you go beyond that, cycles are in some sense, the only minimal non-separable graphs. You cannot remove anything from them to keep them non-separable. If you remove any edge from a cycle, then the graph will no longer be non-separable. So what we'll do is we will construct the Peterson graph from this cycle in steps. Okay? And at each step, we will ensure that we have a non-separable graph. Okay? So let's just do that. So what I will first do is I will add this path. And this is called adding an ear. We are going to add an ear at a time. And an ear in this context is going to be a path. Okay? We start with a cycle, but then we keep adding paths one by one. Okay? So let's say we add this path. Okay? So now we have this much. And now I want to add more stuff. Let me put the new thing in red color, let's say. So the first thing I added is this. Now this one is already there, and I want to add some more stuff. Okay, so what could I do? Well, maybe I'm going to add something here. Okay, so this is my new ear. Both of these graphs are also non-separable. We will prove that. Okay, now let's add something else. So I already have these things in the graph. I've already added this much. And now I want to add one more ear. Okay, so let me use red color again. Let me introduce this last vertex, which has not been added yet. And let me join this here. Okay, and now I have covered all of the vertices of the graph. There are some edges of the graph that are not yet included. So I can add all of them one by one, but instead of adding them one by one, I'm just going to add them all together in the interest of time and space. Okay, so I'm going to do multiple ear additions at one time. So what are the edges I already have? I have this edge, I have this edge, and I have this edge. There are some more edges remaining. Let me add all of those edges one by one in this drawing. So maybe I will start with the red colored edge. Then I will add the blue colored edge. Okay, that is it. Right, so I needed to do two more ear additions. I did them in one drawing. Okay, so what we got here, we got a sequence of graphs, which are all subgraphs of the original graph. So let's call this G0, G1, G2. Then we got G3. Then we got G4 when I added the edge E. And then I got G5 when I added the edge F. Sorry. G5 when I added the edge F, blue colored. And finally, I got the Peterson graph G6. Okay, this is our original graph G. The point here is that all of the graph G0, G1 up to G6 are non-separable subgraphs of the graph G. And in this sense, we were able to generate the Peterson graph from the simplest non-separable graph, which is a cycle. And at each stage, we were able to maintain the property that the subgraph we have is a non-separable subgraph of the Peterson graph. Okay? Good. So is it clear why this is a generation theorem, why this is a generation technique for non-separable graphs? I have not yet written down the theorem or anything, but is the general idea clear? Are there any questions about what we are trying to do? Okay, if not, then let's write down some stuff. Okay. Okay, so what is an ear? Here is the visual you want to have in mind. You have a subgraph and you are adding the path to it. Okay, and this looks like an ear. This is your ear. So let F be a subgraph of a graph G. An ear of F in G, so it's a bit of a mouthful, is a non-trivial path. By non-trivial, I mean it has at least two vertices, so it could be one edge, for example. It is a non-trivial path P in the graph G whose ends lie in the vertex set of F, but is otherwise disjoint from G. What I mean by that is the vertex set of P intersect the vertex set of F is exactly the ends of the path P, and the edge sets of the two are completely disjoint. Okay, so if you look at this drawing here, think of okay, so what you want to do is you want to think of there being a big graph G. You have some subgraph F, and now what you're doing is you're adding a path P to that subgraph. Well, we are not adding, we are just defining what an ear is. So it is any path of the original graph whose both ends are in the subgraph F, but is otherwise completely disjoint from the subgraph F. So it does not share any other vertices or edges with the subgraph F. So in this sense, let's go to this example here, G2, this graph. So think of F as your black colored subgraph. Black subgraph of the Peterson graph G. Okay, G is Peterson. Then for this black colored subgraph of the graph G, what you see in red color in this drawing is an ear of G2 or F in the graph G. Does that make sense? So the red colored path is an ear of the black colored subgraph in the graph G. Okay, so it's a bit tricky because the ear is not part of the F itself. Okay. Anyways, this is just terminology to make things easier to say. All right. So now let's put a proposition. So there are a bunch of things we need to prove. So sure, I showed you an ER decomposition of the Peterson graph, but what guarantees the existence of such an ER decomposition? That is what we are trying to prove now, right? And so the first step in that direction is the following. Supposing I take a non-trivial proper subgraph of any non-separable graph G. Okay, remember this is a proper subgraph. So in particular, f is not equal to G. That is what we mean by proper subgraph. Then the claim is that there is always going to be an ear for this subgraph in the graph G. In the proposition, f is not non-separable. However, as far as we are concerned, we only need the proposition when f is non-separable. So we only care for the case when f itself is non-separable. However, the proposition does not require that assumption. So the way you want to think about is you want to think with this assumption, but we will not use this assumption to prove it. So think about there being a non-separable subgraph of a non-separable graph. Okay, so f is your subgraph and G is your big graph. What this proposition is saying is that there is always an ear in this graph with respect to the subgraph you have chosen. So there is always a path, an ear you can add to this subgraph. The next proposition will prove that when you add this ear, you will get another non-separable subgraph. Okay, so let me actually write down the next proposition before proving either of them. And we may not have time to prove them today. Proposition 5.7. If f is a, now we are going to use the assumption that f itself is non-separable. If f is a non-separable proper subgraph of a graph G, and P is an ear of f in G, then the claim is that if you take f along with P, f union P, this is another non-separable subgraph. Okay, good. So let's see how much time we have now. We have 4 more minutes. Okay, so we will actually be having time to prove this. This one, 5.7, is an exercise. And I will give you a hint. Use theorem 5.2. What was 5.2 again? Can somebody remind me? If I remember correctly, 5.2 says that any two edges belong to a cycle, if and only if the graph is non-separable. Okay, so using that, you can prove the second proposition. Is it clear what the proposition is saying? Because otherwise, of course, we can't prove it. Are there any questions regarding the statement of proposition 5.7? I'll go through it once again. You have a non-separable proper subgraph of the graph. So let's go to an example. Supposing we are looking at this drawing here of G2. So you have a non-separable proper subgraph, which is G2 of the graph G. Now you're adding an ear to it, P, which is the red colored path. Then the proposition is saying that whenever you do this, you get another non-separable subgraph of the original graph. So the fact that it is a subgraph of the original graph is clear. That follows from definitions. What you need to show is that it is a non-separable graph. Okay, so that is the content of proposition 5.7. And in the remaining 3 minutes, I think we will be able to prove proposition 5.6. Okay, so let's go back to the statement. We have a non-trivial proper subgraph of the graph G. We want to show that there is an ear in the graph with respect to this subgraph. Okay, so let's make a drawing. So we have this graph G, and let's say we have a subgraph of the graph F. Okay, so this is the drawing I'm going to use. There is an easy case, which is when the vertex of F is equal to the vertex set of G. So easy case, if the vertex set of F is equal to the vertex set of G. Okay. Right. There is a fact that we will be needing. So there is an easy fact that I'll again leave as an exercise. If you take a non-separable graph, if H is a non-separable graph, and you add a link to that graph. So what is a link? It is an edge that is not a loop. Okay. Then the resulting graph will be non-separable. Then H plus XY, actually, do we need this? Sorry, we don't need this. We are not trying to prove proposition 5.7. Sorry, we don't need this, my bad. Yeah, we are trying to prove proposition 5.6. Okay, so that just requires proving that there is an ear. Okay, so if the vertex set of F is equal to the vertex set of G, then there has to be an edge in G which is not in F. Okay, because F is a proper subgraph of G. Okay, so then there exists an edge F which is in G but not in the subgraph F. Okay, so what does your drawing look like? You have a F and you now have an edge in the graph G which is not already present in F. Okay, and this is an ear of F in G. Observe that F is an ear of the subgraph F in the graph G by definition. It is a path, single edge, with both ends in the subgraph, but the edge itself is not in the subgraph, and that is an ear. Okay, so not so easy case. Supposing the vertex set of F is indeed a proper subset of the vertex set of G. So supposing you have not covered all of the vertices of the graph. So there are vertices in G that are not in F. Okay, then what do we do? So then let's see. So we know that there are vertices here. This is not empty, the vertex set, and this is also not empty. By that I mean the vertex set. Okay. Well, the graph is connected. Since the graph is connected, there has to be an edge going like that. Since G is connected, there exists an edge xy such that x is a vertex in F and y is a vertex in G that is not in F. Now what we are going to do is we are going to delete the vertex x. Let us delete this vertex. And because this is a non-separable graph, the remaining graph will still be connected. Since G is non-separable, the graph G minus X is connected. What that means is that I can go from Y back to this part of the graph. Okay, so which means that there exists a path. There exists a path P in G minus X such that P has ends Y. Y is one of the ends of the path. and another end is going to be some z. P has ends y in the vertex set of G minus vertex set of F, and Z in the vertex set of F. And I can also ensure that the only vertex set of F and P that is common, the only vertex that is common is Z. I will end the path as soon as I reach this side. Right? So I will not keep extending the path. And now observe that P plus the edge xy. So now what is our ear? The ear is going to be the path along with the edge. So we're going to take this path. Oh, I meant to color, sorry. Right, so we're going to take the path along with the edge xy, and that is going to be our ear. Observe that P plus xy is an ear of F in the graph G, and that is our proof. Okay, so I've gone about 4 minutes over time. I'm sorry for that. This is the end of the proof of proposition 5.6. Are there any questions or concerns? It was a bit fast, but it's actually a fairly straightforward proposition to prove. Any questions or concerns regarding the proof or the statement of the proposition? Okay, if not, then what I want you all to do is I want you all to think about proposition 5.6 and 5.7. Try to prove 5.7 yourself using theorem 5.2 or any other way you like, and see what this means. What do these propositions mean in the context of this example? How are these propositions supporting the example that we looked at? And I want you to think on your own what the ear decomposition theorem is going to look like. Okay, we will discuss the theorem tomorrow. We'll write it down. But essentially, we have already proved the theorem. The two ingredients are already there, and that is actually all we need. You just have to fit the pieces together and figure out for yourself what the theorem is going to look like. And we will discuss it tomorrow. Okay? And you will see on assignments, definitely on assignment 2, for instance, the wide applicability of ear decompositions. And those who took my course previously, they have already seen it. So there'll be some amount of repetition, but we will move on to topics that are actually new for all of you. Okay. Any other questions, concerns? I'm here for another 5-10 minutes, so please feel free to turn on your mic and ask any questions you have. Is this example clear to everyone? Is it clear what's going on in this example? Okay, I suppose that is a yes. And am I audible?
Yes.
Good, thanks. All right. So if you go back to this example, you can see why this is a decomposition of the graph. You can see that, well, let's see, how do I want to explain this? It's okay. The lecture is already over, so I think I should only explain it tomorrow. So I assume some of you may not have seen air decompositions before. Could you let me know? Could you maybe type in the chat box and let me know if you have seen air decompositions before or not? Not seen before. Okay, thank you. Thank you, Shani. Anyone else? Not seen. Okay, thank you, Ravi. Okay. Okay, so if there are no more questions or concerns, please feel free to leave the meeting. Maybe I should stop recording. I forgot to do that.